Thank you all for coming. This is a massive room. So today we will have 6 great invited talks, panel discussion, and a selection of posters and spotlight presentations. I don't have much to say, but welcome Ian Goodfellow from OpenAI. He will be giving the first talk of today, an introduction to generative adversarial networks. Thank you, Ian.
Good morning. Thank you, everybody, for coming. I guess I'll explain first a little bit what my goals for this talk are. I know that there's a lot of different people here at the workshop, and the main purpose of the talk is just to give everyone a little bit of context so that you know what adversarial training is, what generative adversarial networks are. If you were at my tutorial on Monday, you probably will have seen a lot of these slides before. But I'm also going to throw in a few new ideas just so that you feel like you got something extra for your time. But this talk is mostly for the people who have just arrived at the workshop and need some context. So this workshop is about adversarial training. And the phrase adversarial training is a phrase whose usage is in flux. And I don't claim exclusive ownership of the phrase, but to avoid confusion, I thought I'd comment a little bit on how the phrase has been used before and how it's mostly used now. So I first used the phrase adversarial training in a paper called Explaining and Harnessing Adversarial Examples. And in that context, I used it to refer to the process of training a neural network to correctly classify adversarial examples by training the network on adversarial examples. Today, other people have started using the phrase adversarial training for lots of different areas. Almost any situation where we train a model in a worst-case scenario, where the worst-case inputs are provided either by another model or by an optimization algorithm. So the phrase adversarial training now applies to lots of ideas that are both new and old. The way that we use the phrase adversarial training now, it could apply to things like an agent playing a game against a copy of itself, like Arthur Samuel's checkers player back in the 1950s. So it's important to recognize that when we use the phrase adversarial training today, we're not only referring to things that were invented recently, but the usage has expanded to encompass a lot of older things that also had other names like robust optimization. Most of today's workshop is about a specific kind of adversarial training, which is training of generative adversarial networks. In the context of generative adversarial networks, both players in the game are neural networks, and the goal is to learn to generate data that resembles the data that was in the training set. The reason that we call the training process for generative adversarial networks adversarial training is that the worst case input for one of these networks is generated by the other player. And so one of the players is always trained to do as well as possible on the worst possible input. It's worth mentioning that there are other works going on in the space of adversarial training where the goal is still to train on adversarial examples, inputs that were maybe created by an optimization algorithm to confuse the model. And you will see some posters about that here. There's also some work about that in the Reliable ML workshop. But I hope that clears up any confusion about the term adversarial training. So generative adversarial networks are mostly intended to solve the task of generative modeling. The idea behind generative modeling is that we have a collection of training examples, usually of large high-dimensional examples such as images or audio waveforms. Most of the time we'll use images as the running scenario that we show pictures of in slides because it's much easier to show a picture of an image than to play an audio waveform. But everything that we describe for images applies to more or less any other kind of data. So there are 2 things you might ask for a generative model to do. One is what we call density estimation, where given a large collection of examples, we want to find the probability density function that describes those examples. But another thing we might do is try to learn a function or a program that can generate more samples from that same training distribution. So I show that on the lower row here, where we have a collection of many different training examples, in this case photos from the ImageNet dataset. And we'd like to create a lot more of those photos. And we create those photos in a random way, where the model is actually generating photos that have never been seen before, but come from the same data distribution. In this case, the images on the right are actually just more examples from the ImageNet data set. Generative models are not yet good enough to make this quality of images, but that's the goal that we're striving toward. The particular approach that generative adversarial networks take to generative modeling is to have two different agents play a game against each other. One of these agents is a generator network, which tries to generate data, and the other agent is a discriminator network that examines data and estimates whether it is real or fake. The goal of the generator is to fool the discriminator, and as both players get better and better at their job over time, eventually the generator is forced to create data that is as realistic as possible, data that comes from the same distribution as the training data. The way that the training process works is that first we sample some image from the training data set, like the face that we show on the left. We call this image X. It's just the name of the input to the model. And then the first player is this discriminator network, which we represent with a capital D. The discriminator network is a differentiable function that has parameters that control the shape of the function. In other words, it's usually a neural network. We then apply the function D to the image X, and in this case, the goal of D is to make D of X be very close to 1, signifying that X is a real example that came from the training set. In the other half of the training process, we sample some random noise, Z, from a prior distribution over latent variables in our generative model. You can think of Z as just a source of randomness that allows the generator to output many different images instead of outputting only one realistic image. After we've sampled the input noise Z, we apply the generator function. Just like the discriminator, the generator is a differentiable function controlled by some set of parameters. And in other words, it's usually a deep neural network. After applying the function G to input noise Z, we obtain a value of X, sampled in this case from the model, like the face on the right. This sample X will hopefully be reasonably similar to the data distribution, but might have some small problems with it that the discriminator could detect. In this case, we've shown a slightly grainy, noisy image of a face, suggesting that this grain and noise is a feature that the discriminator might use to detect that the image is fake. We apply the discriminator function to the fake example that we pulled from the generator. And in this case, the discriminator tries to make its output D of G of Z be near 0. Earlier, when we used the discriminator on real data, we wanted D of X to be near 1. And now, the discriminator wants D of G of Z to be near 0 to signify that the input is fake. Simultaneously, the generator is competing against the discriminator, trying to make D of G of Z approach 1. We can think of the generator and the discriminator as being a little bit like counterfeiters and police. The police would like to allow people with real money to safely spend their money without being punished, but would like to also catch counterfeit money and remove it from circulation and punish the counterfeiters. Simultaneously, the counterfeiters would like to fool the police and successfully use their money. But if the counterfeiters are not very good at making fake money, they'll get caught. So over time, the police learn to be better and better at catching counterfeit money, and the counterfeiters learn to be better and better at producing it. So in the end, we can actually use game theory to analyze this situation. And we find that if both the police and the counterfeiters, or in other words, if both the discriminator and the generator have unlimited capabilities, then the Nash equilibrium of this game corresponds to the generator producing perfect samples that come from the same distribution as the training data. In other words, the counterfeiter producing counterfeit money that is indistinguishable from real money. And at that point, the discriminator, or in other words, the police, can not actually distinguish between the two sources of data, and simply says that every input has probability 1/2 of being real and probability 1/2 of being fake. We can formally describe the learning process using what's called a minimax game. So we have a cost function for the discriminator that we call J superscript D, which is just the normal cross-entropy cost associated with the binary classification problem of telling real data from fake data. We have one mini batch of real data drawn from the data set and one mini batch of fake data drawn from the generator. And then if we use this minimax formulation of the game, then the cost for the generator is just the negation of the cost for the discriminator. The equilibrium of this game is a saddle point of J superscript D. And finding this saddle point resembles the process of minimizing the Jensen-Shannon divergence between the data and the model. We can use that to actually prove that we'll recover the correct data distribution if we go to the equilibrium of the game. We can analyze what the discriminator does when we play this game, and we see exactly what it is that allows generative adversarial networks to be effective. The basic idea is that if you take the derivatives of the minimax game's value function with respect to the outputs of the discriminator, we can actually solve for the optimal function that the discriminator should learn. This function turns out to be the ratio between p data of x and p data of x plus p model of x. You can do a little bit of algebra on that to rearrange it, and you get p data of x over p model of x. So we're learning a ratio between the density that the real data is drawn from and the density that the model currently represents. Estimating that ratio allows us to compute a lot of different divergences, like the Jensen-Shannon divergence and the KL divergence between the data and model that are used for training with maximum likelihood. So the key insight of generative adversarial networks is to use supervised learning to estimate a ratio that we need to be able to do unsupervised learning. There are also a variety of other papers by Shakir Mohammed and his collaborators and Sebastian Noisen and his collaborators that talk a lot about the different divergences that you can learn with these kinds of techniques and how this estimation procedure compares to other techniques that have also been developed in the statistical estimation literature previously. But this is the basic idea right here, is that we're able to learn this ratio. So far I've described everything in terms of the minimax game. I personally recommend that you don't use exactly that formulation, but you use a slightly different formulation where the generator has its own separate cost. And the idea is that rather than minimizing the discriminator's payoff, the generator should maximize the probability that the discriminator makes a mistake. The nice thing about this formulation is that the generator is much less likely to suffer from the vanishing gradient problem. But this is more of a practical tip and trick rather than a strong theoretical recommendation. And some of the other speakers you'll see today might actually give other advice. So it's kind of an open question about exactly which tips and tricks work the best. One of the really cool things about generative adversarial nets is that you can do arithmetic on the z vectors that drive the output of the model. We can think of z as a set of latent variables that describe what is going to appear in the image. And so Alec Radford, the co-organizer of this workshop, and his collaborators showed that you can actually take z vectors corresponding to pictures of a man with glasses, the z vector for a picture of a man, and the z vector for a picture of a woman. And if you subtract the vector for man from the vector for a man with glasses, and you add the vector for woman, you'll actually get a vector that describes woman with glasses. And when you decode small jitters of that vector, you get many different pictures of a woman wearing glasses. A lot of you may have seen a similar result before with language models, where the word embedding for queen could be used to do arithmetic, where if you subtract off the word embedding for female and add the word embedding for male, you get a vector that is very close to the word embedding for king. In this case, Alec and his collaborators have a slightly more exciting result because they not only show that the arithmetic works in vector space, but also that the vector can be decoded to a high-dimensional realistic image with many different pixels all set correctly. In the case of language modeling, the final result was a vector that was very near the word for king, but there was no need to decode that vector into some kind of extremely complicated observation set that corresponds to a king. Probably the biggest issue with generative adversarial networks, and to some extent with other forms of adversarial training, is that the training process does not always converge. Most of deep learning consists of minimizing a single cost function. But the basic idea of adversarial training is that we have two different players who are adversaries, and each of them is minimizing their own cost function. When we minimize a single cost function, that's called optimization, And it's unusual for us to have a major problem with non-convergence. We might get unlucky and converge to a location that we don't like, such as a saddle point with a high cost function value. But we'll usually at least converge to some general region. When we play a game with two players and each of them is simultaneously trying to minimize their own cost, we might never actually approach the equilibrium of the game. In particular, one of the worst forms of non-convergence that we see with generative adversarial networks is what we call mode collapse, or if you're in on a little joke in our first paper, we also call it the Helvetica scenario sometimes. The basic idea behind mode collapse is that when we use the minimax formulation of the game, what we'd really like to see is minimization over G in the outer loop and maximization over D in the inner loop. If we do this min-max problem applied to the value function V, we are guaranteed to actually recover the training distribution. But if we swap the order of the max and the min, we get a different result. In fact, if we minimize over G in the inner loop, the generator has no incentive to do anything other than map all inputs Z to the same output X. And that output X is the point that is currently considered most likely to be real rather than fake by the current value of the generator. So we really want to do min-max and not max-min. Which one are we actually doing? The way that we train models, we do simultaneous gradient descent on both players' costs. And that looks very symmetric. It doesn't naturally prioritize one direction of the min-max or max-min. In practice, we find that we often see results that look an awful lot like max-min, unfortunately, with G in the inner loop. So using some very nice visualizations from Luc Metz and his collaborators, we see here that if we have a target distribution we'd like to learn with several different modes in 2 dimensions, the training procedure, shown in the bottom row of images, actually visits one mode after another instead of learning to visit all of the different modes. So what's going on is that the generator will identify some mode that the discriminator believes is highly likely and place all of its mass there. And then the discriminator learns not to be fooled by the generator going to that one particular location. And instead of learning that the generator ought to go to multiple locations, the generator moves on to a different location until the discriminator learns to reject that one too. One way that we can try to mitigate the mode collapse problem is with the use of what we call mini-batch features. This is introduced in the paper that we presented on Monday night from OpenAI, where the basic idea is to add extra features to the discriminator so that the discriminator can look at an entire mini-batch of data. And if all the different samples in the mini-batch are very similar, then the discriminator can realize that mode collapse is happening and reject those samples as being fake. On the CFAR10 data set, this approach allowed us to learn samples that show all the different object classes in CFAR10 for the first time. On the left, I show you what the training data looks like for CFAR10. You can see that it's not that beautiful to start with because there are only 32 by 32 pixel images, so the resolution is very low. On the right, we see the samples that come from the model, and you see that you can actually recognize horses, ships, airplanes, and so on, and cars, that we actually have the real object classes recognizably occurring within this data set. On ImageNet, there's 1,000 classes, so it's much more difficult to resist the mode collapse problem. On ImageNet, our model mostly produces samples that have kind of the texture of photographs, but don't necessarily have rich class structure. But we do occasionally get rich class structure. If I show you some very cherry-picked examples, we're able to make lots of different pictures of things like dogs, spiders, koalas, bears, and birds, and so on. We still see a lot of problems with the model, though. In particular, we often see problems with counting. We think that this might be something to do with the architecture of our convolutional network, that it's able to test whether a feature is absent or present, but it doesn't necessarily test how many times that feature occurs. So we see things like this giraffe head with 4 eyes, this dog with something like 6 legs, or this kind of 3-headed monkey thing, or stacks of puppies rather than a single puppy, or a cat with 1.5 faces. We also often see problems with perspective, where the model generates images that are extremely flat. In particular, the image on the lower left looks to me like somebody skinned a dog, like a bearskin rug, and then took a picture with the camera looking straight down at it on the ground. Or the picture in the lower middle looks to me literally like a cubist painting, where in the cubism movement, artists intentionally removed all the perspective from an image and rearranged the object to show its different parts from different angles, but representing the entire thing as flat. In many cases, we see images that are really quite nice, but have some problem with the global structure. A lot of the time, this just consists of images of animals where we don't actually get to see their legs, that they have a head and torso attached, but they don't actually complete the legs anywhere. And in my particular favorite generator sample so far in the lower left, we have an image that we've actually named Fallout Cow, where we have an animal that is both quadrupedal and bipedal. It actually has legs, and it has the right number of them, but it has two different bodies. So what are some things that you can do with generative adversarial networks? There are just so many different things that it's a little bit hard to show all of them. I showed a lot more in my tutorial, but I can show you just a few really quick. One thing that came out recently is image-to-image translation. This is from the research group at Berkeley. And the basic idea here is to take a conditional generative adversarial network and map from one domain to another. It can do things like take images that say for every pixel where the different, what kind of class should appear at each pixel, and turn that into a photorealistic scene with the desired objects in the desired positions. It can also take an aerial photo and turn it into a map, or it can take a sketch of an object and turn it into a photo of an object. More recently, there was a very exciting result that finally developed the ability to generate realistic samples on the ImageNet dataset from all 1,000 classes, and with really good diversity. This result is called plug-and-play generative models, and it combines many different approaches to generative modeling, including generative adversarial nets, moment matching, denoising autoencoders, and Langevin sampling. The results are just really excellent, and we see lots of different very recognizable, high-quality images with all the right numbers of legs and everything. So generative modeling has really come very far in just the last month, actually. And generative adversarial nets are part of that progress. I have a few comments about exactly what it is that allows generative adversarial networks to work well on kind of an intuitive level. One of the main things that's really different about generative adversarial nets compared to other approaches to machine learning is that they give a very nice way of telling the model that there are multiple correct answers. So a lot of the time with supervised learning, we use something like mean squared error to tell the model what its output should have been. So on the left, I show a little bit about what's wrong with the mean squared error training process. Suppose we have the blue dot at the bottom of the slide representing some input. And we'd like to learn to map this input to some desired output. Suppose all the different green dots represent different possible outputs that are all valid. Well, in the training set, suppose that the label that we had for this particular blue dot was the green dot on the far left. But suppose that the model produced the green dot on the far right. Mean squared error will induce the red error arrow saying that instead of producing the dot on the right, the model should have produced the dot on the left, which is the one that appears in the training set. And that means that over time, the blue dot will actually get mapped to something more like the mean of all these different green dots. And that causes us to learn things like blurry images when we try to learn to predict different images associated with some input. Generative adversarial networks don't actually directly use a pair of inputs and outputs to tell the model what it should do. Instead, the discriminator learns how inputs and outputs can be paired, and then the discriminator tells the model whether it did a good job or not. So the discriminator would ideally learn that all of the different green dots are possible options, and then when the generator produces the green dot on the right, the discriminator says that that was a good thing to do. There are many different good things that the model can do, and the discriminator will hopefully endorse all of them. So we now have this mechanism for saying that many different outputs are possible, instead of always steering the model toward one predefined answer. We can see this especially in the context of next video frame prediction. So this paper by Bill Lauder and his collaborators shows what happens when we use a few different kinds of models to predict the next frame in a video. On the left, I show the ground truth, where we have this 3D rendered image of a person's head. And you can see that the image is very sharp and has a clearly visible ear. Using a model that was trained with mean squared error in the image in the middle, we see that the ear has vanished because the exact location of the ear is not especially predictable. And when the model averages over many different possible places the ear could go, it vanishes. Similarly, the eye has become blurry. In the image on the right, we see what happens when an adversarial loss is included in the training process. In this case, the model is now encouraged to produce samples that actually look realistic, and it knows that there are multiple different answers that are all possible. So it's been able to choose one of the many different sharp images that could happen at the next time step. It's also worth thinking about what adversarial training looks like for people. And really, the way that the idea of adversarial training emerged was that economists and other researchers in those kinds of fields were already working on thinking about the way that multiple different agents acting in a market have their behavior influenced by the process of them optimizing their own payoff while all the other players optimize their payoffs. So some things that I think could be interesting to look at from a machine learning point of view are whether cycles in markets can be explained by the failure of optimization algorithms to converge. If we have trouble fitting generative adversarial nets and we have complete information, just think about how hard it is to choose prices for goods when there are many more actors and when you don't have complete information about the market. I'm sure this has been studied to some extent, but I think that bringing the economists and the machine learning people together could find some more interesting ideas that we didn't already know about. We've also seen lots of cases of things like auctions that are designed to make sure that people pay the right price. And that's more or less what I was thinking of when I designed generative adversarial nets. One last comment is that if we think about the way that people learn, researchers like Ericsson have shown that the way to become really good at any particular task is to practice it a lot, but also to do deliberate practice. You're not just putting in a lot of hours. You are specifically choosing subtasks within the skill that you're trying to get good at that are especially difficult for you, and getting feedback from an expert who coaches you. You can think of adversarial training as capturing both of these aspects of developing a skill. Rather than just training on lots and lots of training examples, you're training on the worst case inputs that are really hard for the model. And in the case of generative adversarial networks, you have an expert, the discriminator, coaching the generator on what it should have done instead. So a lot of insights from human psychology and human learning are actually telling us how we can make machine learning more effective. So in conclusion, adversarial training is a way of training a variety of models in different ways that all involve working on a worst case input. Generative adversarial nets are one of the most popular members of this framework, and they're based on using the estimate of a ratio of densities to do unsupervised learning. And part of why they work so well is that they allow the model to have multiple correct answers, and they draw on a lot of the ideas that help humans to learn really well. I'm almost out of time, but I think we might be able to have a few questions, if that's okay with the organizers.
You have several microphones on the sides.
Okay. Yeah. So I have a question first here, over here. So I'm just curious. For sequential data like video, do you know any work of using maybe recurrent network that actually can generate the sort of sequence of data to generate a video, or what kind of challenge that would be?
Yeah, there is a paper about generating videos with generative adversarial networks. I forget the exact title off the top of my head. There's a paper here at this workshop today called Unrolled Generative Adversarial Networks. And I know that one of their experiments involves using a recurrent network to generate MNIST 1 pixel at a time. So you could check out their spotlight and poster.
And how about generating language sequence of words in discrete domain?
The thing that's difficult about that is the discrete outputs, which mean that the generator is not differentiable. So that's an open research area. It might be solvable using things like the reinforce algorithm to do policy gradient on the parameters, or using things like Gumbel softmax or the concrete distribution. Or it might be possible to generate word embeddings from the generator and then decode them to discrete values instead of generating the discrete values directly.
And how about the speech, which is continuous? We know that Google's WaveNet use different mechanism of generating speech. And do you think this GAN framework can be used equally well?
Yeah, so before I left Google, I suggested that they try generating continuous waveforms with GANs. And I don't actually know if they tried and the GANs didn't work, or if they just went straight to using pixel RNN type methods to generate the continuous waveform. Okay, but so I do think that the continuous waveform is the way to go with GANs.
Okay.
If that did work, the advantage that GANs would have over WaveNet is that the GANs can generate the sample much faster. That WaveNet needs to pass through a neural net for every single sample of the audio. So it's generating really thousands of samples using thousands of passes through the network. And it takes about 2 minutes to generate one sample, 1 second of audio. Okay, the GAN could generate a long waveform in one shot.
It's interesting to see that WaveNet didn't really have the kind of blurring effect that you show over there using mean square error kind of criterion for the image. So do you have an explanation why one's blurred, the other one is not blurred?
So the blurring effect is with mean squared error in real valued spaces. And they were using discrete spaces where they have a softmax distribution. So their loss function is not actually mean squared error. It's categorical cross entropy.
Okay, but that's still not as good as GAN.
Let us ask another question. You can chat with Ian later. Yeah. Any other questions? Okay, thanks, Ian.